Hi, my name is Rotem Ulaev. In this talk, I'm going to present my work on the implicit bias of SGD via dynamical stability analysis. This work was done in collaboration with my advisor, Tomer Michaeli, as well as Daniel Sudri, Mor Spiegel, and Greg Onji. Neural networks show remarkable generalization in many applications. The performance level usually depends on the number of parameters in the model. Here we have an experiment where a neural network was trained with an increasing number of parameters. The horizontal axis is the number of parameters, and the vertical axis shows the classification error. Let's start by looking at the underparameterized regime, in which the network doesn't have the capacity to perfectly fit the training set. As expected, when the number of parameters increases, the error on the training set, shown here in dashed line, gets smaller. However, the test error in solid line has a U shape, which agrees with the classical bias variance trade-off. This is the classical behavior expected from underparameterized model, which can't interpolate the training data. But what if we exaggerate and use far more parameters? Obviously, in the overparameterized regime, the training loss goes to 0, which means that the model perfectly fits the training data. Yet, the test error also decreases. In fact, the generalization only gets better even without regularization, which contradicts classical wisdom. Specifically, in the overparameterized regime, there are multiple global minima, all achieve 0 loss. The vast majority of them correspond to models that don't generalize well. So we expect from the trained model to fail on the test set. But somehow, the standard training procedures we use result with good models. Why is that? Let's take a closer look at this phenomenon. Assume that we are in the overparameterized regime, and our objective is to fit a piecewise linear model to these training points. In such setting, a perfect fit is feasible. For instance, a possible interpolating function is this green line. However, it is not unique. The red function also interpolates the data. While both functions achieve 0 loss on the training set, they can have different test errors. Somehow, the optimizers we use consistently avoid converging to bad solutions. This begs the question, how does the optimizer tell apart good minima from bad ones if they all have a 0 training loss? In the past, it has been recognized that the optimizers we use have biases towards certain solutions. Moreover, it was proposed that the implicit bias of gradient descent can be expressed as some regularization term that is added to the training loss. This turned out to be true for several settings, such as overparameterized linear regression with a quadratic loss, matrix factorization under certain assumptions, linear classification on separable data, and so on. But recent work has pointed out that this is not true in general. Specifically, they show that often for neural networks, there is no regularization term that can explain the implicit bias of GD. Additionally, these results are independent of the step size. This is while such dependence is clearly seen in practical settings. For example, we trained a shallow ReLU network to fit this training point using GD with various step sizes, starting at the same initial point. Here we see the solutions that GD converged to for each step size. Clearly, the learning rate has a strong effect on the solution. Okay, so in contrast to previous work, in this work, we rely on a property of SGD which always holds. Additionally, as opposed to existing results, our results are sensitive to the learning rate. Our approach is based on the concept of dynamical stability. So let's do a quick overview on the dynamical stability of gradient descent. Here we have two minima, one sharp and one flat. Near a flat minimum, the gradient is small and therefore GD gradually approaches the minimum. However, near a sharp minimum, the gradient is large and therefore GD escapes the minimum. This illustrates that flat minima are stable for GD. Now, analyzing the stability of the full nonlinear dynamics is often intractable. However, it was shown that in the vicinity of a minimum, we only need to consider the dominant term in the Taylor expansion to determine stability. At the minimum, the gradient is zero, and therefore the dominant term is the second order. Using this expansion, GD dynamics become linear. In other words, GD on the second order approximation is just a linearization of the full dynamics of GD. Then it is easy to show that the linearized dynamics of GD is stable if and only if the second derivative at the minimum is less than 2 over the step size eta. Throughout this talk, when I say stability, I mean the stability of the linearized dynamics, which in many applications is sufficient to determine the stability of the full dynamics. That was the stability criterion for the one-dimensional case. But what about higher dimensions? In higher dimensions, the second order Taylor expansion at the minimum is the quadratic form over the Hessian matrix, which is positive semi-definite. In this case, all we care about is the sharpness of the sharpest direction. The sharpest direction is given by the top eigenvector of the Hessian, and the sharpness in this direction is given by its top eigenvalue. Therefore, a minimum is stable for gradient descent if and only if the top eigenvalue of its Hessian is smaller than 2 over the step size eta. Namely, lambda max less than 2 over eta is the exact stability criterion for gradient descent. Now, what about stochastic gradient descent? Until our latest work, the exact stability criterion was unknown. However, it is easy to show that this condition of GD is necessary for the stability of SGD. So, in the first part of this talk, we will use this simple condition to study the implicit bias of SGD. Yet, note that this condition is independent of the batch size and therefore doesn't fully characterize the behavior of SGD. In the last part of this talk, I will present our latest work on the exact stability threshold of SGD. Overall, we see that SGD is biased towards minima, whose Hessian eigenvalues are smaller than 2 over eta. While this fact is well known, the effect that it has on the trained model was not fully understood. So we saw that stable minima are flat enough with respect to the step size. These can affect both the predictor functions that the trained model implements and the implementation itself. In this talk, we will go over the following topics. We will start by looking at the effect of dynamical stability on the predictor functions that the model implements. We will first develop our intuition using simple models with univariate input. Then we will move on to models with multivariate input. We will see that the dynamical stability constrains the solution to be a certain type. Afterwards, we will take this analysis one step further. Specifically, we're all familiar with the universal approximation theorem that states that shallow networks can approximate arbitrarily well any continuous function over compact sets. However, stable minima can correspond only to a specific set of functions. Then we can ask, what is the class of functions that stable solutions can approximate? Here we will see some interesting results. Then we will go on to talk about the effect of dynamical stability on the implementation. Specifically, for most models, every predictor function has infinitely many different implementations. In this work, we want to isolate and reveal the effect of dynamical stability on the implementation. Therefore, we will focus on a setting in which there is only one optimal functionality of the network, and all global minima are just different implementation of the same function. Then we will ask, what are the properties of stable implementations? I will finish by presenting our latest work on the stability threshold of SGD. As I mentioned earlier, until our latest work, the exact stability threshold of SGD was unknown. In the past, people proved multiple results on the stability of SGD. However, these results are either bounds on the stability threshold or implicit conditions from which we can't draw conclusion on the behavior of SGD. Here, I will present for the first time the precise stability criterion in closed form, and I will show you some insights on SGD in light of these results. These topics are covered in 4 papers with the following references. So let's start with the first topic. So let's consider a univariate shallow ReLU network with K neurons, where the input and output of the models are scalars. In the set of all functions that can be implemented by this network is given by this expression. We denote this set by calligraphic F. It is easy to see that this set contains only piecewise linear functions with at most K knots. We use the quadratic loss. Additionally, we focus on the overparameterized regime where the number of neurons K is larger or equal to the number of training samples N. In this regime, we can achieve zero loss. Namely, we can always find a solution that interpolates the data. In fact, there exist infinitely many different solutions. The question is, to which solution SGD can converge? To answer this, we need to determine which solutions are stable. A major challenge in this analysis, however, is the implementation ambiguity. Specifically, any optimal solution can be implemented in various ways. For instance, we can multiply the weights of the first layer by some positive constant and divide the second layer by the same constant. This results in different implementation of the same predictor function. The problem is that in parameter space, one implementation can correspond to a flat minimum, while another corresponds to a sharp minimum. So what determines whether SGD can converge to a certain function? Obviously, it can't converge to a function if none of its implementation is flat enough to be stable with respect to the step size. Formally, we define omega of f to be the set of all parameter vector of theta that implement the function f. Then we're interested in the flattest implementation of f. namely the minimum of the top eigenvalue of the Hessian over all implementations of F. So how flat is the flattest implementation? In our work, we prove that the sharpness of the flattest implementation is bounded from below by this expression. We recognize this integral as a weighted L1 norm of the second derivative of f. Specifically, the weight function g depends only on the x-coordinate of the training data. As can be seen in this example, G is non-negative and typically has its mass concentrated at the center of the data. Furthermore, G decays towards the extreme data points and vanishes beyond them. Now, if F is a stable solution, then it must be that its flattest implementation has a sharpness not greater than 2 over eta. This fact leads us to the following result. If F is a stable solution of SGD, then its second derivative has a bounded weighted L1 norm. Importantly, the bound depends on the step size. As the learning rate increases, the set of stable solutions contains less and less non-smooth functions. Recall that most of G's mass is located at the center of the training data. This implies that stable solutions tend to be smoother near the center of the data distribution and less smooth near the edges. Overall, we get that training with a large step size leads to smoother predictors. Let's go over a simulation that demonstrates this result. Here we see the training data on the left and its corresponding weight function g on the right. In this simulation, we trained a neural network using GD with various step size, starting at the same initial point. When trained with a small step size, GD converges to this block function on the left. On the right, we see the second derivative of the function, which can have high values. However, even in this with this very small step size, where the weight function is high, namely high penalty, the second derivative is small. When trained with a medium step size, GD converges to this blue function. Now the solution is much smoother, particularly at the center of the data. This trend continues as we increase the learning rate. Note that in this case, the green function is flat at the center, but have relatively high second derivative outside the support of the training data. This demonstrates that while dynamical stability restrains the solution on the support of the training data, it imposes no restrictions on the function outside the support. The previous simulation that we went over is part of a bigger experiment where we scanned the step size over a wide range while starting at the same initial point. The red line shown here marks the edge of the stable region, which is 2 over eta, meaning that GD cannot converge to a minimum that has sharpness above this line. Now we add to the plot the sharpness of the minimum to which GD converged in practice. We can see that these two lines coincide. This means that GD converged at the edge of the stable region. In the past, it was shown that converging at the edge of stability is the typical scenario in neural networks training. Additionally, for each network we trained, we determined the sharpness of its flattest implementation. This is presented by the blue line here. Finally, this purple curve depicts our lower bound on the sharpness. Recall that our bound is simply the weighted norm of the function of the second derivative of f. Therefore, we see that f indeed gets smoother as the step size increases. This simulation validates our theoretical result. Okay, this concludes the univariate case. Next, we move on to networks with multivariate input. So here we have the same model as before, single hidden layer with ReLU activation, but this time the input is a d-dimensional vector. Therefore, the set of all functions that can be implemented by this network is given by this expression. We again consider the overparameterized regime where the number of neurons k times the input dimension d is greater than the number of training samples n. Before I give you the result for this case, it's important to point out that the univariate result shown here naturally extends in radon space rather than in primal space. Yet, we still manage to derive a similar result for the multivariate setting in primal space as well. In comparison, we see that the second derivative in the univariate result is replaced by Laplacian of f, which is the sum of the second derivative across all coordinates. Here, both weight functions rho and g depend on the training data. However, rho doesn't have the properties that we expect from a standard weight function. For example, it can have negative values as well as singularities. However, this turned out to be okay. Specifically, we show that the integral of rho over any hyperplane is non-negative and finite. Since the Laplacian of f is supported on hyperplanes, we have that for our purpose, rho can be viewed as a legitimate weight function. Now, as the learning rate increases, the bound gets smaller, and the set of stable solution contains less and less non-smooth functions, which is similar to the univariate case. Therefore, also in the multivariate case, we have that large step size implies smooth predictors. Let's illustrate this result. Here we have the training points in blue and an interpolating function in gray, which correspond to some single hidden layer ReLU network. The Laplacian of f is the sum of Dirac delta functions supported on lines, where the amplitude of each delta is color-coded. On the right, we have the corresponding weight function rho for this training set. Then the integral in our result is just a weighted sum of line integrals over rho according to the Laplacian of f. We validate our result with an experiment on MNIST. Specifically, we took two classes from MNIST and trained a single hidden layer network with ReLU activation to classify for classification using SGD. Here we see the same behavior from the univariate case, namely that f indeed gets smoother as the step size increases. In the same experiment, we also measured the test accuracy. Here we plot the test accuracy against the norm of the second derivative. We see that where the norm is small, namely smooth predictor, the accuracy is large. This experiment validates our intuition that smooth predictors generalize better. Okay, let's take this analysis one step further and talk about the approximation power of stable solutions. In the context of approximation power of neural networks, the most famous result is the universal approximation theorem. This result states that shallow networks can approximate arbitrarily well any continuous function over compact sets, as long as their activation is non-polynomial. For example, here we have a blue function f and a sequence of approximators fk realized by ReLU networks in orange. As we increase the number of neurons, this sequence converges to the blue function. Then the universal approximation theorem says that single hidden layer networks can approximate in such a way any continuous function on compact sets. Although these approximations are theoretically guaranteed, as we saw in practice, dynamical stability allows to converge only to certain functions. So we ask, what is the approximation power of stable solutions? To answer this, we first denote the convex hull of the training set by H. Then we show that if a sequence of stable functions converges to some function, then the limit function is also stable, namely its weighted L1 norm of its Laplacian is bounded with respect to the step size. The important conclusion from this result is that if a limit function is not stable, then it can't be approximated by stable networks. Now, as when we decrease the step size, more and more functions satisfy this inequality. Here we ask, is there a continuous function that is not stable for any positive step size? And the answer is yes. Specifically, let's focus on the pyramid function f, which is shown here for the two-dimensional case. Under the assumption that the support of f is contained in the convex hull of the training points, we prove that the weighted L1 norm of f's Laplacian is unbounded. Sorry. This means that there is no positive learning rate to bound this L1 norm. In other words, the function f is not stable for any positive step size. Therefore, by the form above, this pyramid function cannot be approximated with stable depth 2 networks. Yet, in the same time, we show that this function has a stable depth 3 implementation. Here we have a visualization of this result. The blue area represents the set of all continuous functions over a compact set. And within this set, we have the pyramid function f. Then the universal approximation theorem states that depth 2 networks are dense in this space. That is, they can approximate any function in this set. We showed that stable depth 2 networks can approximate only a strict subset, as f doesn't have a stable approximator. However, depth 3 networks can stably realize this function. Therefore, we have a depth separation, namely the class of functions that stable depth 2 networks approximate is different than that of stable depth 3 networks. This result showcases the importance of depth in training neural networks. So we saw that a single hidden layer network can't stably approximate any continuous function. Here, we ask, can we guarantee approximations for a smaller set of functions? In this context, we show that if a function is sufficiently smooth in Sobolev sense, then it has stable approximators. This means that shallow networks can approximate smooth functions in practice. Okay, until now, we talked about the effect of dynamical stability on the implementation that the network, the effect of dynamical stability on the function that the network implements. Now, we will talk a little about the effect that it has on the implementation. Since we don't have much time, I will give you just an overview of this work in a high level. Here, we look at the following setting. We consider deep linear networks in which each layer performs a multiplication by a matrix without an activation functions. And we focus again on the quadratic loss. Recall that our goal is to study the effect of dynamical stability on the implementation and not on the functionality of the solution. Then under a mild assumption, in this setting, there exists only one optimal functionality of the network to which all global minima correspond. Therefore, in this setup, dynamical stability affects only the implementation. To study the properties of stable minima, we choose to examine the flattest minima as representatives. So here we show that the flattest minima gets sharper linearly with depth. In other words, all minima gets sharper as we increase the depth. This means that training a deep model without tricks such as normalization layers and so on can be quite challenging. Our second result characterizes the flat minima through the norm of the features in intermediate layers. Generally, this norm can be arbitrary, as one layer can amplify the signal by a large factor, and the next layer can compensate this by multiplying the input by a small factor. However, we show that in flat minima, this cannot be. Specifically, we show that in flat minima, the propagating signal experiences a balanced gain throughout the network. Okay, our last result in this setting shows an interesting phenomenon of layer coupling. Specifically, we show that in a flattest minimum, any two consecutive layers have a common singular vector. Overall, we have that flat minima correspond to balanced networks with coupled layers. Now, we move on to the final topic of this talk, which is the stability threshold of SGD. So let's go back to the beginning of this talk. We said that the exact stability criterion of GD is the top eigenvalue of the Hessian be less than 2 over eta. Yet, for stochastic gradient descent, this is only a necessary condition for stability. So up to this point, all the results that I show you on the implicit bias of SGD are based on this necessary condition, as the exact condition was unknown at the time. In the past, many studies analyzed the stability of SGD and gave some result in this context. However, a closed form expression for the exact threshold was missing until now. So when we talked about stability, we used the minimum's sharpness as a metric. Here we run an experiment in which we trained a neural network using SGD with various step sizes and batch sizes on the MNIST dataset. For each pair of hyperparameters, we measure the sharpness at the minimum to which SGD converges. We see that for large batches, the sharpness equals 2/eta, which is the stability threshold of SGD, of GD, sorry. This is the stability threshold of GD. Yet, for small batches, the sharpness is quite far from 2/eta, indicating that the top eigenvalue of the Hessian may not be the right measure for the stability in the general case. Here, we ask, what is the stability criterion of SGD? To answer this, we use the following setting. We consider a general objective function that is just an average of some loss functions, one for each training sample. SGD's update rule is given by this equation, where B is the batch size. We assume that the batches are drawn uniformly from the training set independently across iterations. To study the dynamical stability in this setting, we again use linearization with these notations. Here, HI is the Hessian of the ith function, and H is the full Hessian of the loss, which is the average of the HIs. Our goal is to find the exact threshold such that the mean square distance to the minimum is finite if and only if the step size is below this threshold. And we have this exact result. Specifically, we proved that the mean square distance to a minimum is finite if and only if the step size is below the threshold shown here. This threshold resembles that of GDs of 2/lambda max, yet with a different matrix, C pseudo inverse D. These matrices are given by these expressions, where O times denotes the Kronecker product and O plus denotes the Kronecker sum. The matrix C is independent of the batch size and depends only on the full Hessian. The dependence on the batch size comes through the matrix D, where we have a convex combination between two matrices with parameter P. The left matrix, H Kronecker H, is associated with the full batch SGD, namely gradient set. Whereas the right matrix, which is the average of HI Kronecker HI, is associated with single sample SGD. When the training set is much larger than the batch size, P goes like 1/B. So to this top eigenvalue, we call the generalized sharpness. So let's go back to the experiment from the beginning of this topic, while focusing on batch equals 1, batch size equals 1. Here we see clearly the gap between 2/eta and the sharpness at convergence. However, our theory says that we need to consider the generalized sharpness and not the standard sharpness. Since calculating the generalized sharpness in this experiment is practically impossible, we computed a lower bound on it. This lower bound turned out to be very close to 2 over eta. From this result, we can learn two things. First, the fact that the lower bound in purple goes along with the red line proves that our theory correctly predicts the stability threshold of SGD. Second, the generalized sharpness is somewhere between these two lines in the green area. Since in some places it has to be very close to 2 over eta, we can conclude that SGD converges at the edge of the stability. Namely, we also have an edge of stability phenomenon with SGD, but with a different stability threshold. We also show that the stability threshold that we found is non-decreasing with the batch size. This means that decreasing the batch size can only reduce stability. The final result in this talk deals with the role of the batch size, and it does so through analogy. Here we show that SGD has the same stability threshold as another algorithm. Specifically, here we define a new stochastic optimization algorithm where in each iteration it takes a gradient step with a batch of one sample with probability P and a gradient step with a full batch with probability 1 minus P. Then we show that the stability conditions of SGD and this algorithm are the same for P given here. Again, when the number of samples n is much larger than the batch size, we have that P goes like 1 over the batch size B. Therefore, this result implies that in the context of stability, even moderate batch sizes make mini batch SGD behave like GD. To summarize, SGD converges to flat minima. Flat minima correspond to smooth predictor functions as well as balanced implementations. Finally, stable solutions are not universal approximators. Thank you for listening.